In this chapter section, you will learn how to calculate pH and pOH of weak acids and weak base. Please read the OER textbook for chapter section 14.7 for more details. In the previous section, you learned how to calculate pH and pOH of strong acid and strong base. Those are pretty straightforward because strong acid and strong base fully ionized. That means the concentration of the strong acid would equal to the concentration of proton. So you can take the negative log of that concentration of proton to get pH. And for the strong base, it's fully ionized as well. So that means the concentration of the strong base would be the same as the concentration of hydroxide. When you take a negative log of the concentration of hydroxide ions, then you will get the pOH. However, for the weak acids and weak base, they only partially ionize when dissolved in water. This means when any of these acids and base dissolve in water, they're only going to produce less than 100% of hydronium ions and hydroxide ions. For example, weak acid hydrofluoric acid, when it's dissolved in water, it will only partially dissociate into hydronium ions. The arrow that I have here is not correct. Can you change it to the reversible arrow because it indicates the weak acid? Again, because this is a weak acid, so that means if you have 100 molecules of hydrofluoric acid, it will produce only less than 100 molecules. So if you have 2 molar hydrofluoric acid, the amount of hydronium ions that is produced will also be less than 2 molar as well. Same idea applied to weak base ammonia. When ammonia dissolves in water, it's going to accept proton from water to become ammonium ion and produce hydroxide ions. Again, because this is not one of the 6 strong base, so that means this is a weak base. So that means if you start with 100 molecules of ammonia, the reaction will produce only less than 100 molecules of hydroxide ions in the solution. Same as if you start with 2 molar concentration of ammonia, then the hydroxide ions concentration will be less than 2 molar. To differentiate between acidic solution and basic solution, I know that the reason why HF is an acid because it donates proton to water and also at the end it produces hydronium ions. And I know that the reason why this is the base because the base accepts proton from water and is also produce hydroxide ions. So that means whenever that you see species that produce hydronium ions or proton, you can say that that species is an acid. And if the species produce hydroxide ions in the solution, we can say that that species is a base. So far for weak acid and weak base, we know only qualitative amount of the hydronium ion and hydroxide ions that will be produced. For example, for weak acid, the amount of hydronium ions that will be produced would be less than the weak acid concentration. And for weak base solution, the amount of hydroxide ions that will be produced would be less than the concentration of weak base. But in order to calculate for pH and pOH, we need to know exact available concentration of hydronium ions and hydroxide ions. So the goal for this chapter section is to find what is the exact amount that available in the solution. Note that the weak acid and weak base ionization, they both are in equilibrium. So that means in order to find out how much exactly the amount of hydroxide ions and hydronium ions are available, we will need to look at their concentration at equilibrium. So next we are going to take a look at the relationship between the equilibrium constant of acid, pH, and the concentration of hydronium ions. Let's take a look at the acid ionization of dihydrogen phosphate ions react with water. Again, in order to write out Ka expression, it indicates that these have to be the equilibrium constant of an acid. So that means this species have to behave as an acid, which means the acid will need to transfer proton to water to produce hydrogen phosphate and hydronium ions. Therefore, the dihydrogen phosphate behave as an acid, and its conjugate base would be the hydrogen phosphate ions. And on the other hand, water accepts proton. So in this case, water would behave as base. And the conjugate acid of base water would be hydronium ions. And the Ka expression for this reaction would be Ka equal to the concentration of hydrogen phosphate multiplied by concentration of hydronium ions and divided by concentration of dihydrogen phosphate. This Ka expression allow us to either calculate for Ka value when all of these species are given, or use Ka value to actually determine the amount of hydronium ions at equilibrium. For example, if the reaction reach equilibrium and the pH has been determined to be 3.6, we can actually use this pH at equilibrium to calculate for the concentration of the hydronium ions. In order to calculate for the concentration of hydronium ions or proton, it will equal to 10 to negative pH. After plugging in the value, you will obtain a concentration of hydronium ion equal to 2.5 times 10 to negative 4 molar. So to find out the Ka value of this acid, you can just plug in the value of the conjugate base that is given, multiplied by the concentration of hydronium ions and divide by the concentration of the weak acid. And you will get the Ka value of 6.3 times 10 to negative 8. And as you see, the Ka value is very small, as indicated this acid is a weak acid. Note that at equilibrium, the amount of conjugate base and conjugate acid are the same because again, these two are given 1-to-1 ratio. So that's why the concentration of these two come out about the same. So far you see how to calculate Ka from the given pH and the given value of each of those species at equilibrium. Next, we are going to use the Ka value to help us determine the concentration of hydronium ions at equilibrium and eventually to calculate for the pH of weak acids. Recall from Chem 122, in order to find out the concentration of something at equilibrium, you will need to set up Rice table. Rice table stands for reaction, initial, change, and equilibrium. Let's take a look at pH calculation of weak acid, acetic acid. To calculate for the pH of this weak acid solution, first, we will need to determine the concentration of proton at equilibrium. Again, 1 molar acetic acid is not the concentration of the proton because this is a weak acid, so it's only dissociate partially. So that means it's going to dissociate to be less than 1 molar. To find out the concentration of proton at equilibrium, then we will need to use Rice table and given Ka value to help us for that. Step 1, you will need to write out the balance reaction for the weak acid ionization in water. Start with weak acid, react with water. You will see that acid transfer proton to water. Then the acid will then become its conjugate base, acetate ion, and as water accepts proton, it becomes its conjugate acid, hydronium ion. Next, for step 2, then you will need to start set up Rice table. Rice table start with reaction, which what we just determined, and followed by the initial. The initial concentration given from the problem is given the concentration of weak acid, acetic acid, to be 1 molar. Because water is in liquid phase, so it doesn't matter because we will not include water in the Ka expression. For the two products you see, the initial concentration of these two will equal to 0 because at the beginning, before the reaction starts, there should be no products produced. Next, change. When things undergo changing in a chemical reaction, it have to follow stoichiometric ratio. For example, if 1 mole of acetic acid react with water, is going to produce 1 mole of acetate ion and produce 1 mole of hydronium ion. But because this is a weak acid, so we don't know exactly how much it undergo change, that's why we will leave it as X. So that means 1X of this will convert to 1X of acetate ions and 1X of hydronium ions. The negative side tells us that over time, the concentration of acetic acid decreased. and the positive side tells us that over time, the concentration of acetate and hydronium ions increased. After it's undergo change, whatever left, that would be the concentration at equilibrium. Here is the summary of Rice table. Next, to solve for the concentration at equilibrium, you will need to set up the Ka expression, which is come from the concentration of the product divided by of the reactant. Note that this concentration must come from the equilibrium concentration only because we are using the equilibrium constant Ka. Next, plug in given value of Ka, 1.77 times 10 to negative 5 that the problem gives, and plug in the concentration from the equilibrium point, which is X and X for acetate and hydronium ions, and 1 minus X that come from concentration of acetic acid at equilibrium. When you start distributing the number, you will get the equation that involved with X and X squared. In order to solve for X and X squared, you will need to use quadratic equation, which is not very convenient. So we are going to simplify this instead. In order to simplify it, we need to use the approximation. When you look at Ka value of 1.7 times 10 to negative 5, it tells us that this reaction doesn't go far to the right. It's actually pretty much stay as the reactant. That's why the Ka value is very small. It tells us that at equilibrium, the majority of the species that predominant is the reactant. The small value of Ka tells us that very small amount of 1 that undergo change. So that means if you compare between negative 1x to the initial concentration of 1, the negative 1x is going to be insignificant compared to the initial concentration of 1. However, if you look at the product, because the product starts with 0, when it's gaining an x, these two x are still going to be significant. If you remember, the analogy that I use in Chem 122 to explain this concept is that, for example, if you have $1 million, you lose just $1, that $1 is insignificant compared to $1 million. Versus if you have $0, when you gain $1, that $1 is significant. Now, after you ignore the negative x compared to 1, then you can solve for x squared and eventually solve for x. The x value, if you refer back to the Rice table, is the concentration of hydronium ions at equilibrium. So to solve for pH, then you do negative log of the concentration of hydronium ions, then you will get the pH of 2.375. To check your answer, this solution is an acidic solution, so that's why your pH come out should be less than 7. A weak base is analogous to weak acid. You can use Kb and Rice table to solve for pOH, and then eventually you can solve for pH of the base solution. To calculate pH and the hydroxide concentration of methylamine, first you will need to write out the base ionization in water. Methylamine will react with water by accepting proton from water and become its conjugate acid. And then water, since it loses proton, is going to then become hydroxide ions. Again, this is a base because it accepts proton and also is produced hydroxide ions at the end. Next, set up Rice table the same way that we did before with the weak acid. Start with the initial concentration of weak base. And the concentration of the product will be 0 at the beginning because there is no reaction yet. Then when it's undergo change, because the stoichiometric ratio is 1 to 1 to 1, so that's why when the methylamine undergo change, negative x is going to decrease and the product will increase by 1x, and at equilibrium would be whatever that left over from the initial and the change. Here is the summary of Rice table. Next, you will need to set up Kb expression. Again, the difference between Ka and Kb is Ka belong to acid. You will see hydronium ions in the expression. However, Kb is for the base, so that means you will need to see hydroxide ions in the equation. Next, use the concentration at equilibrium, plug in to this Kb expression, then use the approximation to simplify the calculation and then solve for x. The x value is the concentration of hydroxide ion at equilibrium. And if you take a negative log of the hydroxide concentration, then you are going to get pOH. But the problem asks for pH, so that means you will need to do one more step, converting pOH to pH by subtracting from 14. Again, even though the problem doesn't specify the temperature in this case, we are going to assume that it's out of 25 degrees Celsius, so that's why we should be able to use the 14. And this is a base solution, so your pH should come out to be greater than 7. Now let's pause the video to complete example 1 and 2. When you finish, you can resume the video again and check your answer against my answer. Example 1 asks us to calculate pH of propionic acid. This acid is not one of the 6 strong acids, so that means this acid is a weak acid. For the weak acid, the concentration of proton is not going to be the same as the concentration of weak acid. This is when you will need to set up Rice table and use Ka value to solve for the concentration of proton. The concentration of proton at equilibrium then can be used to calculate pH. First step, let's start with set up Rice table. For the reaction, we need to write the acid ionization of propionic acid. React with water. For propionic acid, the acidic proton is the hydrogen that connected to oxygen. The acid will transfer this proton to water and become conjugate base propionate ions and hydronium ions. Next, fill out the initial. The given initial concentration of propionic acid is 0.095 molar. Ignore water because water doesn't include in the Ka expression. At the beginning of the reaction, the concentration of the product should be 0 molar. Next, fill out change. Because we don't know how much it undergo change, so we are going to use X as the unknown variable. For the reactant, when the reactant undergo change is going to be a negative because over time, the concentration of the reactant decreased. However, for the concentration of the product, over time is going to increase by X amount, so it's going to be positive X. This reaction is in 1 to 1 to 1 ratio, so that's why the change would be X to X to X ratio. Again, the equilibrium concentration would be whatever left from the initial and change, that would be the equilibrium concentration. When you fill out Rice table, make sure that the value that go into Rice table have to be in unit of molar concentration. Next step is to set up Ka expression, which equal to the concentration of the propanoate multiplied by the concentration of hydronium ions and divide by the concentration of propanoic acid. Then fill out the Ka value and the concentration at equilibrium for all of those species. By looking at the equation to solve for x, you can see that if you distribute all of these, you are going to end up with x squared and x. This is the quadratic form that you need to use to solve. In order to simplify this, we will need to use approximation, which means that we are going to ignore the negative x in comparison to 0.095 because the Ka value is very small, indicate that the negative x is insignificant compared to 0.095. Then you will get the simplified equation, which is 1.3 times 10 to negative 5 equal to x squared divided by 0.095. So for x squared and do the square root to get x, and you will get the value of x equal to 1.1 times 10 to negative 3. The x value tells us the concentration of hydronium ion at equilibrium. So if you take negative log of the concentration of hydronium ions, then you will get pH of the solution, which equal to 2.95. This solution is an acidic solution, so the pH of the solution have to be lower than 7. Example 2 asks us to find pH of methylamine solution, and is given Kb value of this solution. Kb imply that this species have to behave as a base, and if you look up the 6 strong base, This is not one of the 6 strong base, so this must be the weak base. Therefore, to find out the concentration of hydroxide ions for a weak base at equilibrium, you will need to also set up Rice table and use Kb to find out the concentration of hydroxide ion at equilibrium. Then you are going to convert that to POH, then eventually convert that to pH. So first, let's start with set up Rice table. For the reaction, we need to write the base ionization in water. We will react methylamine with water. Weak base methylamine then will accept proton from water. The species that is accepting it is the lone pair of nitrogen, so that means we are going to add one more hydrogen on the nitrogen. Because water transfer proton to methylamine, so now water will become hydroxide ion. If you compare between example 1 and example 2, you can see that for acid, again, it will always produce hydronium ions, but for the base, it will always produce hydroxide ions. Next, let's fill out the initial concentration. Initial concentration of weak base is 0.33 molar. We can ignore water, and the concentration of the product would be 0 and 0 molar. For the change of reactant would be negative X, the change of the product would be positive X. And the equilibrium concentration would be whatever left from initial and change. Next, set up Kb. Kb for this reaction would be concentration of conjugate base multiplied by the concentration of hydroxide ions and divided by the concentration of weak base. Next, fill in the Kb expression with the Kb value and the concentration at equilibrium. Next, we will use approximation to avoid quadratic equation and solve for x. X equal to 1.2 times 10 to negative 2. X is the concentration of hydroxide ion at equilibrium. If you take negative log of the hydroxide concentration, you will get POH. This problem doesn't give us the temperature condition, so we are going to use the standard temperature, which is 25 degrees Celsius, and relate pH and POH by the 14. And you will get the pH would equal to 14 minus POH. Plug in the value of POH, you will get pH equal to 12.08. Since this solution is a base solution, so the pH of this solution should come out greater than 7. Please practice more of this concept by doing the DIY that I provide here. And you can get help during the Hangout session as well, and you can work with your peers. The answer key will be posted on Moodle after the Hangout session. Thank you.